Now that we understand the important step of model building, let's see how to evaluate a machine learning model for its performance. As we talked about overfitting earlier, we know that we have to be careful not to overfit. With overfitting, our model kind of learns by heart the example that we give it, without learning the true signal, without learning the true pattern that we want it to learn. So in this case, to evaluate the performance of our model, we use cross-validation. To use cross-validation, what we need to do is the first step is to shuffle the examples. We do that to make sure that there is no impact of a particular ordering of examples and that it doesn't influence the way we will estimate the performance of a model. We shuffle them. Then we split it into three distinct sets. This has to be distinct, meaning that for each example is either in the first set or in the second set or in the third set. No example should be present in more than one set. This is also why we said at the beginning that it's important to remove duplicate in the data. Because once we split our dataset in three distinct sets, we don't want any example to be in more than one set because we will not have the good estimate of our model. The first set is the training set. The training set, as the name suggests, is for model training. This is the example that the model will see to learn. And the second one is called validation set. This one is used for tuning hyperparameters and for choosing the model according to the strategy that we just saw. It is important to have a third set, which is called the test set, to have an independent evaluation of the final model that we wish to base our decision on. That is, for this task, this model performs the best. Think of the case where we have a lot of hyperparameters and values that are possible per parameter. As we iterate over the possible combination, let's say we train thousands of models, it will be the case that one will outperform the other, but maybe by pure chance. Training a model is a repetitive process. If we keep on training the model on the same data with much more repetitions, this goes without saying that the model performance will increase, but so is the chance of overfitting. We need to evaluate how much a model performs on the examples or the dataset that it has never seen before, and this is actually the use case of machine learning. This is why we use the trained model on the test set to have an independent evaluation of our trained model because we want to understand what performance we can expect from the data that the model have never ever seen. This is the representation of what will happen when we deploy our model. Post deployment, the trained model is expected to perform in a similar manner because it will face the examples that it has never seen before. A good practice is to split the data in three distinct sets before the beginning of the pipeline. The reason to do so is to avoid the accidental information leak from the training set to the test set. If we have such an information leak, then the original purpose of having a test set is lost. We want the test set to be independent and to be able uh, uh, there for testing the model's true performance. In worst case, if such leak happens, then if we overfit to the training set, we will also overfit to the training set as well. And of course, the test set will not be representative of what will happen when we deploy our model. Let's see what other things that we need to remember in model evaluation step. Okay, one thing also is to choose an appropriate metric for our problem. This is important in the sense that sometimes a metric will measure, as we saw in the beginning, some acceptable and unacceptable behavior. It is important to choose a metric that will represent what we finally want to report, let's say to our boss or to the people that will use it. If we report some accuracy, we only report the ones that the model achieved on the test set because this is the final one. Also, we can compare the model performance with a baseline. A baseline is a point of comparison which can be the performance of the simplest algorithm that we can think of, or it can be a comparison with random labeling as well. For example, what happens if we randomly label emails whether they are spam or not? Does our algorithm performs better than this random labeling? Let's say that we have the same amount of spam emails and as the emails that are not spam. So this 50% becomes our baseline of accuracy. If our model performs at 50% accuracy, then it is not useful because it doesn't do better than just randomly labeling an email without having any prior information. Another baseline can be human performance. Obviously, not for classification of cats and dogs, but for example, if it is difficult to classify an X-ray scan for a bone rupture, so we can compare the performance of a trained machine learning model with the human performance in this case. Also, class imbalance is something to be careful with. Class imbalance is a problem when we do not have the same amount of examples in one class in comparison to another. A classic example for class imbalance is credit card fraud prediction, where we have some transactions that are made from a credit card and we want to predict whether it is a fraudulent transaction. Fortunately, we don't have the same amount of fraudulent transactions in comparison to the real ones. What we expect generally is 1% or less of such transactions among all. Imagine that we chose to report the performance of our credit card fraud prediction model in terms of accuracy. If we do so, then even if we predict every transaction as non-fraudulent, we will have 99% of the accuracy because the model is correct 99% of times due to the actual number of real transactions, which is 99%. If we have to think about 99% accuracy, it seems to be exceptionally good, but it doesn't have any relevance in this particular case. Probably we should go for specificity or recall that we talked about in our previous lecture. Since we talk about overfitting and underfitting in model evaluation, let's recall what these are. Underfitting and overfitting, both the concepts are of concern when we talk about model evaluation. Please refer to the previous lecture where we discussed in detail about both the concepts. Just for a refresher, underfitting refers to oversimplification of the data, while in overfitting, the model, apart from fitting to the relevant data, also fits to the noise in the data. Let's see how to detect these. This part as well we have covered in the previous lecture in detail. I advise you to please refer to the previous lecture where we discussed all these concepts. Just to recall, we can detect it by comparing the average error that can be computed in the training set or validation set or test set. Generally, we care about the ones in the test set, but if we are tuning hyperparameters, we can use the ones in the validation set or the training set. This is important because it helps us to choose the model and the hyperparameters more wisely. Because if we are in the case of overfitting, it means that our model is too complex. Let's say that a decision tree of 1000 depth is probably too complex and kind of just remembers the examples that it has trained on, and hence overfitting and not learning the true patterns. Maybe we want to tune our hyperparameters differently. Also, in case of underfitting, probably uh, we need to have a model that is comparatively complex, allowing us to learn on comparatively complex patterns in the data. Now, one important thing in model evaluation is to be aware of data leakage. Let's try to understand in detail. We discussed in context of different sets that no example should be present in more than one set. Data leakage is a related concept that we need to be very careful of. In case of data leakage, in the context of machine learning, the evaluation of our metric will be bad, also indicating that we will not get the same prediction performance when the model will face an unseen example after its deployment. There can be many scenarios where a test set contains information present in the training set. One example can be in the case of image classification, where a test set may contain similar images to the training set. Another example of data contamination can be related to features. Let's say in case of house pricing, we receive the data from the agency, um, which also gave us additional information, let's say agency fee numbers. That is how much was the fee of the agency when the house was sold. Now we know that the agency fee is directly dependent to the price of the house. Usually agency charges a few percent of the house price as their fee. This feature should not be present if we do not know the price of the house. In case agency fee numbers are present in the test set, the model will perform exceptionally good because it has the future information, which should not be present while predicting the house prices. Data leakage or data contamination or presence of future information should be taken care of while evaluating machine learning models. Now let's come back to the machine learning project lifecycle and see the next step in detail.